Sum number 4. Let n be the set of natural number and let R be a relations on n cross n. R is a relation on n cross n. Earlier we used to have R as be relations defined on n, a or set of integer. This time we are defining n R, the relation R on n cross n, defined by AB related to CD, ordered pair AB related to ordered pair CD, if and only if A into D equals to B into C for all ordered pair AB and CD belonging to n cross n. Correct? Now this sum is slightly different from the sum which we have been doing. In the previous sums, all those previous sums, you will observe the relation R is defined either on set A, on natural number, on the set of integers. But this time, instead of defining the relation on set of natural number or n, it is defined on n cross n. It is defined, relations R is defined on n cross n, meaning your R will be a subset of n cross n cross n cross n, right? Because if R is a relation defined on A, then we say R is a subset of A cross A. So if R is a relation defined on n cross n, then R will be a subset of n cross n cross n cross n, right? Meaning the elements of this particular relations will be something like this. The components itself are ordered pair. Clear? Slightly different from what we have been doing. So here AB, this AB is related to the CD. AB is related to CD if A into D equals to B into C. This AB, this ordered pair AB, or the components itself are ordered pair AB is related to CD. AB related to CD, this particular element. I'll take this as the first component, the first element, second component, second element. AB, ordered pair AB related to ordered pair CD if A into D equals to B into C. Extreme meets. For all now elements here, elements for n cross n's will be ordered pair. Correct? Now to prove that this relation R defined on n cross n is an equivalence relation, right? To prove this is an equivalence relation, I need to complete this in 3 steps to prove R is first reflexive, R is symmetric, and R is transitive. Start with the reflexive. R is reflexive. To prove that R is reflexive, what you have to do is do this for all AB belongs to n cross n. You have to prove that AB is related to AB, right? Because earlier when R was defined, R be relation on n, then we used to define reflexive as A related to A, means ordered pair AB belongs to R, right? Now here, since R is defined on n cross n, I have to prove that ordered pair AB is related to ordered pair AB. Meaning AB belongs to R. Correct? Means AB is related to AB because the elements are this time ordered pair. Correct? So to prove that R is reflexive, we have to prove that for any arbitrary AB belongs to n cross n, to prove that AB is related to AB. Correct? Let's prove this. Can I write AB equals to BA? I can always write commutative nature. 2 into 3 equals to 3 into 2. Right? Now look at this. A, B, C, D. A, B, C, D. If A, D equals to BC, then AB is related to CD. So I can write A, B, C, D. I can always write AB is related to A, B, C, D. C is A and D is B. So I can write this also as AB. A, B, C, D. A, B, C, D. So A is related to B, C is related to A, ordered pair AB is related to ordered pair CD. Now CD here is AB. Correct? So AB related to AB because AB equals to BA. Therefore, the relation R is reflexive. Correct? Next, symmetric. To prove that R is symmetric, what I have to do is for AB related to CD, AB related to CD, to prove CD is related to AB. AB related to CD, from this I can write AD equals to BC. Bring this to this side and this to this side. BC equals to AD, or let me write this as CB. I'm doing adjustment, nothing but adjustment, so that I can use this property. Now look at this one. CB equals to DA, means C, this is A, this is B. CD will be related to AB. CD will be related to CD related to AB. CD related to AB. CD related to AB. I started with AB related to CD. I got CD related to AB. Therefore, R is symmetric. R is symmetric. Right? Next, transitive. To prove that R is transitive, what I have to do is AB related to CD, CD related to EF, to prove AB related to EF. From the first I can write, use a different color. From the first I can write AD equals to BC, and from the second one I can write CF equals to DE. Multiply this to AD CF equals to BC DE. Cancel this to AF equals to BE. So I can write AB equals to EF. Using this property, AB equals to EF, mean AB equals to AB related to EF. Started with AB related to CD, CD related to EF, and I have proof AB related to EF. AB related to CD, CD related to EF, and I could write AB related to EF. Therefore, the relation R is transitive. It's transitive. R is reflexive, R is symmetric, R is transitive. Therefore, R is an equivalence relation. Right?